During the extraction of petroleum, wellheads are a crucial part of a wellhead's overall structure. Without it, the subsurface pressure would result in a constant spout. To control this flow, a wellhead is used to seal the pressure coming from deep underground. The device has valves that slow the release of oil and shut it off when awaiting extraction, or in the case of an emergency. But should the wellhead be damaged in any way, the pressure could result in a devastating eruption, spewing oil across the tundra or ocean in what is known as a blowout. Thankfully, these events are rare, and modern platforms are built with several fail-safes in mind to prevent loss of material and life. But the potential of a blowout is there with every drill site. If a wellhead is damaged and control is lost, teams have to act fast to bring the flow of crude oil under control. While Alaskan oil production has had blowouts in the past that result in minimal damage to structures and pose no risk to the region, the potential of greater consequences happening is something to be taken seriously, since blowouts can take hours or days to be brought under control. With the increased interest in Alaskan oil production, there is also an increased risk of a spill taking place. In order to help the nation achieve its energy goals, it is important to plan for any potential problems that could slow or stall the mining process. Due to the risk it poses to U.S. waterways, the Department of Homeland Security, specifically the U.S. Coast Guard, is charged by federal law with the responsibility of providing oversight for oil spills in coastal regions. By working closely with several other federal agencies, the U.S. Coast Guard ensures oil spill prevention, preparedness, and response regulatory requirements are met by companies operating on the north slope of Alaska. In regions like Prudhoe Bay, many wellheads are located on the tundra or along the coast, sometimes on small islands, and surrounded by ice. Spills will most likely happen above the water surface, thus the spill is going straight onto the tundra, beaches, or into shallow water. Whale migration routes that travel along the coast could be impacted, as well as seal and walrus populations, bird nesting grounds, and fish stocks. As a result, any community dependent on the sea will also find a lot of challenges. The ability to quickly clean and limit the spread of oil has proven difficult with mechanical recovery alone. Thus, the process of different methods of burning has become an alternative way to limit the oil spread on land or water. Through the burning process, the majority of oil is broken down and helps make cleanup efforts more effective. This removes toxic amounts of oil from the surface of the water, which also prevents the creation of emulsions that are particularly difficult to remove from the environment. A faster cleanup doesn't just mean that the wildlife is spared, it means the jobs of the region are minimally impacted and goodwill is maintained among the local inhabitants. There are many things that can cause oil to not be successfully burned, including oil consistency, amount of water present, ocean currents, wind, whether oil is trapped in the ice, and more. But after oil is burned, several droplets can be left behind, and gases can be blown by the wind towards population centers. The size of droplets can change where the remaining oil is likely to end up. Due to water tension, small droplets will usually fall to the bottom of lakes or the ocean, and large droplets will tend to float. Where particles move can pose a risk to the prolonged damage to the food web of the Arctic, which directly impacts the wildlife that is harvested for local subsistence and industry. Because of the many applied response technology variables that need to be considered following an oil spill, ADAC-ARCTIC's Wellhead Ignition research project seeks to help give authorities the ability to confidently make a decision about if and when wellhead ignition may be the best action to prevent a catastrophic oil spill. Built upon past research, this project expands upon the understanding of oil spills while also developing a method to account for new variables, including the source of oil as well as the study of the burning process. The result of the research then contributes to the creation of a coded Python library designed for modeling and evaluating the direction oil will travel and the places it will likely collect, where burned gases will fly, and what communities and wildlife will be impacted. To build the tool, a database of variables is created and plugged into the modeling equations, including the cone of dispersion, burn efficiency, droplet size, currents, and much more. This tool also takes into account the spill's location, the wind, water currents, ice conditions, animal migration patterns, temperatures, and many other factors in order to build a dynamic readout of the unfolding situation, and offers predictions of where the oil and smoke will travel. Once the modeling tool is ready for use, a map of the area will be generated, as well as the likeliness of it traveling beyond the initial bounds. If any villages or endangered animal habitats are at risk, they will be identified so that the appropriate precautions can be made. The tool will then evaluate the downwind potential distribution of burn smoke and gases to help minimize impact, including what days and hours would be ideal for a controlled burn. This helps to protect the local communities who are reliant upon the land or sea for their way of life, and to protect the industry from unforeseen risk.
The main mission of the project is to help the federal, state, and local agencies to formulate a response for the wellhead blowout in the Arctic. And the goals of the project is to assess the feasibility of intentional wellhead ignition. Incorporating that, what we're doing is we're looking at different mitigation measures and see whether the intentional wellhead ignition is one of the better ways to accomplish this, so we don't have the long-term impacts of the oil spill persisting for long periods of time.
The oil industry and also the government regulatory oversight agencies like the Coast Guard, the Environmental Protection Agency, and the State Environmental Protection and Conservation Agencies currently lack modern sophisticated tools that comprehensively evaluate the public health and the environmental impact for wellhead ignition. So what we are trying to do here is to build on older models by adding significantly more variables, updated data that greatly improve the analytical capability overall. This will give government and industry responders alike the best possible model to base important real-time post-oil spill decision-making. It's going to take some time for us to develop the model, establish it, and evaluate it in a controlled environment. So to reach that level of actual use, it's going to take about 2 years to finish. After that, we can start evaluating it.
Alaska has both incredible mineral resources along with some of the richest wildlife harvests in the country. When mining or oil production does anything to damage the harvest of hunters or fishermen, there is a loss of good faith. A good name is crucial in maintaining a good relationship to ensure production is not hindered, and that new regions might be explored into the future with the blessing of the inhabitants. Today, the process may be much faster, but since Alaska continues to be highly reliant upon the wilderness, any damage to the state is directly felt by its inhabitants. Oil remains a cornerstone of the modern economy, and any disruption, especially in a place as vital as Alaska, can ripple across the entire nation. This project aims to provide a practical manual for use during a disaster like an oil spill, empowering the Department of Homeland Security and its enterprise agencies like the U.S. Coast Guard and its federal, state, and industry partners to make more informed, timely decisions. By providing access to precise modeling and guidance, we can enhance the effectiveness of intentional wellhead ignition and many other applied response technologies, all with the goal to protect the environment, uphold public trust, and reduce harm to surrounding communities, making every response safer, smarter, and more successful.